In this video, we will be introducing the nomenclature for ionic compounds, and we will differentiate between naming monovalent, those metals that have only one possible charge, and the multivalent or polyvalent, those metals that have more than one possible type of charge, the difference in the nomenclatures between those two. We will start our discussion with the monovalent metals. These are the metals that have a preferred ionic charge for the particular element that we're working with, which is based on the group number. Elements in group 1 or 2, those are our alkali and alkali earth metals, will take on a charge of +1 and +2 respectively. So anything in our alkali, this first column, is going to always be a +1 when forming a compound, and anything in our group 2, our alkali earth metals, will always have a +2. Note that hydrogen is not included in this. So anything from lithium down will have a +1, and then anything from magnesium down will have a +2. Similarly, there are also common charges for some of the anions that we'll be working with. And this is the case when we're looking at a nonmetal reacting with a metal. So if we have like lithium reacting with a fluorine, or a lithium with an oxygen, or a magnesium with a sulfur, when it's just one element that is a metal reacting with one element that is a nonmetal. In this case, the charge that the nonmetals take is reflected in how far they are from the noble gas. Our noble gas is column 18, or group 18. So our fluorine, chlorine, bromine, and iodine, which are all one away from their nearest noble gas, will take on a -1 charge. Oxygen and sulfur will take on a -2, and nitrogen will commonly take on a -3 when it is bound to just metals. As is the case with the chemical formula, when we are naming things, the cation comes first. So in our chemical formula, the cation is always on the left part of the chemical formula, and the anion is always placed on the right. In the naming, we start with the metal cation, and then add on to that name the nonmetal anion, replacing the end of the nonmetal name with the "ide" suffix. So an example of this would be if we're combining Na sodium with F fluorine. The way that we would write out the name is because sodium is in column 1 in group 1, it can only have a +1 charge. So this is an example of a monovalent metal. So we'll just use the elemental name, sodium, followed by the name for the nonmetal, fluorine, remove the end part of the name of fluorine and replace it with "ide." So it would be fluorine, get rid of the "ine" part, and replace it with "ide." So taking a sodium cation and a fluorine anion, or a fluoride anion, combining them together, we get sodium fluoride, which would be NaF. When we are coming up with a chemical formula, we will often use subscripts in order to balance the positive and negative charge of the ions so that they will equal 0. We need to have a neutral compound for our ionic compounds. Or the charge itself needs to add together to become the overall charge of the compound. So some examples would be if we have a calcium and an oxygen. When we add the two together, we need the charges to balance out. The name would be calcium because calcium is in the second column of our periodic table, so it can only be +2. Our oxygen is a -2, so this is our anion. So the name is calcium oxide. Again, we take the oxygen, remove the last syllable, and replace it with "ide." So it would be, instead of oxygen, it's oxide. So we have calcium oxide. The chemical formula for that would be CaO. And it gets this particular formula because the charge on oxygen, which is 2 away from the noble gas, would be a -2, and calcium is in the second group, so it would be a +2. Another example, if we could have a sodium ion and a sulfur ion, which would be a sulfide, we take the name sulfur, get rid of the part, and replace it with "ide" to give sulfide. So this would be combined together, sodium sulfide. When we add the two together, we need, in terms of the chemical formula, for there to be a 0 charge left behind. Because the sulfur has a -2 charge, that tells us that we will need 2 sets of the sodium in order to balance out that charge. We need 2 sets of +1 to balance out the -2. So the chemical formula for sodium sulfide would be Na subscript 2 to denote that we have 2 sodiums, and then an S. The 2 sets of sodium ions cancel out the -2 charge on the sulfur. Another example would be aluminum. Aluminum can only have a +3 charge. So if we combine aluminum with oxygen to give us aluminum oxide, because of where aluminum is on the periodic table, it will lose 3 electrons to become a +3. Oxygen will gain 2 electrons to become O2-. And so in order to balance out the charge, we will need 2 sets of aluminum to give us a total +6 charge, and 3 sets of oxygen to give us a total -6 charge. Add the +6 and the -6, that gives us a 0. So the overall chemical formula for aluminum oxide would be Al2O3. Lastly, barium chloride. We have a barium, which is a +2, chloride, which is next to the noble gas, gets a -1. So barium with a chlorine would be barium chloride. Barium chloride, the chemical formula would be BaCl2. Now, not all metals are like our alkali and alkali earth metals. Most of the transition metals and a good portion of the main group metals, such as tin or lead, are going to form a variety of different oxidation states, meaning that they can have a bunch of different charges. So copper, for example, can be copper +1 or copper +2. So this is a polyvalent or multivalent metal. It can have multiple different charges, whereas our alkali and alkali earth metals, those in group 1 and group 2, could only have a single type of charge. Anything in group 1 is a +1, anything in group 2 is a +2. So as a result, it is not sufficient to name the compound based on just having the nonmetal and the metal. So we can't just call it copper oxide, for example, because the copper could be either a +1 or a +2, and that will give us 2 different chemical formulas. We could have Cu2O or CuO, depending on the charge on the copper. So when we are naming our multivalent metals, we need to have a way of defining what the charge on the metal is. The way that we will do that is, for naming these, we will start with the metal name, and then we will add on to that, in a set of parentheses, the oxidation state, which is the charge, in Roman numerals of that metal in a set of parentheses. We will then follow it as before with the nonmetal, removing the end of it and adding the IDE suffix. So for example, our CuO would be a copper 2 oxide. That is because in order to have CuO, the O has a -2 charge, so to balance it out on a 1-to-1 ratio, this copper has to have a +2. So the 2 here comes from the charge on the copper. Copper 2 oxide is CuO. Cu2O is copper 1 oxide. This ends up leading to a bunch of confusion, because a lot of students, when they're initially coming to do nomenclature, would see the 2 here and think that this should be copper 2 oxide. That is not the case. The Roman numerals are used to represent the charge on the metal. So because in order to get 2 coppers to balance out the charge on an oxygen, we need that copper to be a +1. So Cu2O is copper 1 oxide. CuO is copper 2 oxide. Couple other examples. Fe2O3 would be iron 3 oxide. The way that you will determine, looking at the chemical formula, what the name is or what the charge on the metal will be is based on what it is bound to. So we know that each one of these oxygens is a -2. So in order to come up with the overall balanced charge, the irons have to be +3 each, right? Because -2 times 3 is -6. If we have 2 irons, the way that we will balance out that -6 that comes from the oxides is by each one of these irons being a +3. +3 times 2 is +6. that will cancel out our charge. So that's how we get iron 3 oxide. Another example would be our manganese 6 oxide. In this case, we have an ion, a remaining charge left over. To determine that this manganese here should be manganese 6, we'll look at the charge on the oxygen. Each one of the oxygens here will have a -2 charge. There's 4 of them for a total of -8. Because we have a remaining charge on our compound, that tells us that 2 of those negative charges are not balanced out by the manganese. They are accounted for here. So we have a total of a -8 coming from the oxygen. 2 are accounted for by the charge. The manganese needs to balance out the remaining 6. So this would be manganese 6 oxide. The overall charge on this particular complex is a -2, which means that the manganese has to have a +6 to balance out all the charges coming from the oxygen. Most of the metals that you will deal with will be in the category that tend to have multiple charges. These lead to multivalent cations once they form ionic compounds. The exceptions to these were on a previous slide. That is, the first group and second group are always +1 and +2 respectively. And then there is a handful of other elements such as aluminum, zinc, cadmium, and silver that have only one charge that they can take on. For all the rest, we have to be able to determine what the charge is to come up with a name. The charges themselves can generally not be predicted from where the element is located on the periodic table. Instead, we need to either get the number from the chemical formula or from the name. Getting it from the name is fairly easy. The charge on the cation will be the same as the value in the Roman numerals. Getting it from the chemical formula, we have to do a little bit of work. So for multivalent metals, these are typically the transition and intertransition metals. Iron, for example, can form a +2 with some compounds or a +3. As we will see in a subsequent video dealing with polyatomic anions, the iron here is going to have a +2 because, as we will see, this SO4, which we will call the sulfate ion, ends up having a -2 charge. So we can tell that the iron here has a +2 because the sulfate ion always has a -2. So because the sulfate has a -2 and it's a 1-to-1 ratio of the SO4 to the Fe, we know that the Fe, the iron, has a +2 charge. In our second example, we have Fe2SO4 3. So we have 3 sulfates. These sulfates each have a -2 charge times our 3. So the sum of all of our sulfates have a -6 charge. The iron needs to balance that out. There are 2 irons. So to balance out the -6 charge, our iron will have +3 each. So in this case, this would be iron 3 sulfate, whereas before this would be iron 2 sulfate. Many of the metals in the P block are going to be multivalent. However, not all of them. Some of the main group metals, such as lead, thallium, and tin, will form more than one type of cation. So again, the way that we will name our binary ionic compounds, those that have polyvalent metals, is we first start with the metal, followed by, in Roman numerals, the charge on the metal, and then after that we will have the particular anion with IDE at the end. So we could have Cu2+, which we would call copper 2, or Cu+, which would be copper 1. So the full name will contain the metal, the charge, and then the anion. So this would be copper 1 oxide, because the charge on the coppers here are +1. This would be copper 2 oxide, because the charge on the copper, in order to balance out the charge on the oxygen, would be a +2. So we take the name of the metal, then in a set of parentheses following the name of the metal, the charge of the metal, followed by the anion with, in the case of something like oxygen or fluorine, we remove the end of the name of the nonmetal and replace it with IDE. Finally, I want to make you aware of an older naming scheme that you might see depending on if you're looking up older literature. The modern naming scheme is the one that we were talking about, where you have the metal followed by the charge. An older form indicates the charge on the metal with various endings on the name. So just like where we were taking the anion, chopping off the end of the name and adding IDE, the older naming scheme took the name of the metal, cut off the end, and added OUS or IC to indicate the charge on the metal. The OUS would be the one with the lower positive charge, and the IC would be the form that has the higher charge. This naming scheme here, this older naming scheme, we will not use. I'm merely bringing this up so that you are aware, if you are looking at older literature, what this generally means. Instead, we will be exclusively focusing on our naming scheme where we have the metal followed by the charge.